Good afternoon, everyone. Thank you all for joining today's Resideo webinar session. Today, we are excited to offer a technical training on hydronic system basics. My name is Jamie Quanroot, and I'm part of the Resideo Sales Training Team. And on behalf of all of us, I'd like to welcome you to our training session today. Before we get started with that technical presentation, I'm going to cover just a few administrative items for you. Please join us every Tuesday at 2 p.m. Central Standard Time, where we give you the opportunity to learn about our products. For a schedule of our upcoming September webinars on a variety of topics, please visit resideo.com/webinars and navigate to the tabs named HVAC and Plumbing to find more information on these webinars. Next week, we are featuring a training on how to optimize your truck in order to prepare for heating season. So be sure to register and join us for that training next week on Tuesday at 2 p.m. Central Standard Time. Additionally, we do record each of these training sessions, and you can find these recorded versions on this same website under the Webinar Recordings tab to reference at any point. And then for those contractors who are joining us for today's live session, and you are interested in earning one NATE continuing education credit, there are just a few things to note. If you provided your NATE ID on your registration form, we are going to submit that information to NATE for your attendance of today's live session, and we won't need any additional information from you at this time. If you did not provide us with your NATE ID on that registration form for today's webinar, and you'd like to receive credit for attending this live session, we do ask that you email your first name, your last name, your NATE ID, and the date of the session that you attended to homes.university@resideo.com within 1 week from today. We do submit this information to NATE 1 week following the close of each session. Any requests that are sent outside of 1 week from today's live training will not be able to be processed. And as a reminder, we can only submit requests for NATE credits when you attend that live webinar session, and we are unable to process requests for watching a recorded version of this training. If you'd like more information about the NATE program, please visit their website at www.natex.org. And then one quick note before we begin our technical presentation today, all attendees are muted. However, if at any point during our technical presentation you'd like to ask a question, please use that Q&A feature that is found in your Zoom webinar controls at the bottom of your screen. We are reserving the last few minutes of our time together today to answer some of those questions. So as we progress through the technical training today, be sure to ask any questions that you have in that Q&A feature so that we can address it at the end of today's session. For today's training, we have Chris Parks, who is the water sales leader for the Western United States, joining us today. And Chris is going to be providing our training on hydronic system basics. So with that being said, take it away, Chris.
Thank you, Jamie. As she had mentioned, today we're going to be going over hydronic system basics. So there's a lot of different topics that we can cover with this. We chose to kind of start with some of the necessary valves and explain where you use them, what to look for, how to set them up, etc. So as we go through, we're going to talk about air elimination and water control. We're going to talk about fill valve and backflow prevention. We're going to talk about pressures in general, so static pressures, how expansion tanks play into that, and then some of the products we have that bundle everything together. And as Jamie had mentioned, just to reiterate, if you have any questions, throw them into the Q&A field at the bottom of your screen, and we will get to them at the end of the training. So jumping into the presentation, a couple of things that we're going to focus on today and where I'm going to start is really the three critical pieces that are on every closed loop hydronic heating system. So those pieces consist of an air elimination device, an expansion tank, and a fill valve and backflow. So with every hydronic heating system, there's always some exceptions because in some situations, you're not going to use that fill valve and backflow. And I'll touch on what that is and when you would use something different. Our current fill valve and backflow offering is, if you're looking at a good, better, best layout, we offer the better and the best, so kind of your mid-level and premium offering. We've got two different devices out there. When you're looking at what this accomplishes, it really is just there to, one, prevent cross-contamination. So when you fill a hydronic heating system and you get it up to, let's say, 12 pounds, you start running it, you never want that water to work backwards into your city. The reason is, once this is filled, there's a good chance you're never going to have to touch that water in that system for 10, 15 years. So I don't know about you, but if I had a cup of water that had been sitting on a counter for 10 or 15 years, I definitely don't want to drink that. So the backflow prevention accomplishes that task. It prevents any water from working backwards. The fill valve is a glorified pressure reducing valve. So that's going to basically set your pressure, and that device right there, these two different devices accomplish both tasks, and we'll get into a little bit of each one. So the first is our FM911. We've had this out for several years. It is very similar to our plumbing DSO6 pressure reducing valves. But if we look at these two different devices, which are shipped in the same package, it includes two parts. First is a BP900 backflow preventer. The second is our VFO6 fill valve. I've got a cross section below so you can kind of see what the guts of this look like. So when I was talking about the backflow prevention, really all a backflow preventer is a glorified double check valve. It has two check valves for redundancy, so that if either one of those checks fails, what you're going to get is you're going to get water bleeding through what's called the vent port. It's basically a drain. So if either one of those check valves doesn't seat properly, if the seats wear or tear, if you run into some weird pressure imbalances, it's designed to actually have water come out of the vent. That's by design. Every now and then we'll get a call asking, you know, well, what's going on with this? I've got water coming through. Chances are you've got something not seating right, and the most common culprit for that is going to be sediment that gets in and sticks that open. Once it goes through the backflow preventer, which is basically a big safety device, it enters our pressure reducing valve, or our fill valve, which in this example is our VFO6. So as water enters, it comes into a spring-loaded diaphragm that allows you to set the pressure at the very top of it. So we use what's called a dial set. It will show the actual pressure rating right at the top. And as you turn that red handle, either clockwise or counterclockwise, you're going to be adjusting the spring tension, which is going to adjust the pressure setting going into the system. So typically on a residential property, you're technically going to have two different pressure reducing devices. The first is a PRV coming into the home to reduce the pressure from, let's say hypothetically, the city delivers 110 pounds. You're going to reduce it to usually 60 to 70 coming into the house for your drinking water system. When you put the boiler fill valve on there, you're actually reducing it again, taking it down to a much lower pressure, somewhere typically around 12 to 15 PSI. Our PRV also has a shutoff built into the bottom. So the little red hand on the bottom, or the red screw on the bottom, is basically a shutoff device. So when you're filling with this, and I'll talk about this a little bit more, the best way to kind of fill through one of these is to open the pressure all the way up. So this particular PRV or fill valve will adjust up to about 50 pounds. So you'll take it all the way up to 50, and as you're doing your initial purge, you're actually going to use the shutoff on the bottom to allow flow or disallow flow based on where you are in the purging process. We also have a black terminal, basically a plug that comes factory installed. You can remove that and install a pressure gauge. I personally am a big fan of putting a pressure gauge right at the source of water coming in, because that's where the pressure enters the system and regulates. That, in my opinion, is the best place to test it. So we allow a port there. You can just unscrew it and install a third-party pressure gauge to verify your pressure coming in. When we step into our premium tier offering, we have our NK300S model. Now, this unit comes with some of the accessories that a lot of times are field installed, one of which is the pressure gauge I was just describing. This already ships in the box. We also have two isolation valves on this product. The reason we have two isolation valves is because this product is completely serviceable. One of the big failures on our fill valves or backflow preventers, and I say ours, but really I mean everybody's, is sediment. As sediment comes through, it sticks in the diaphragm, sticks in the check valve assemblies, and that's really what causes the failure. That's what will allow pressure beyond your setting to enter the system, and that's really kind of the culprit of most of the problems that we see with those devices. So by isolating those check valves, you can take every single part out of there. And I've got an image down here in the bottom right. I'm going to try bringing my mouse over to see if you can see it. But every single piece of this can be taken apart. So in figure 9.22, I'm showing the first check assembly, as well as a large, that number 6 is actually a large stainless steel screen. Every part of this can be taken out, cleaned, and put back together. Because of the isolation valves, it gives you the ability to shut it down without having to drain down any of the system. So it makes it really easy to kind of get in, clean it if you need to, and put it back together. We also have 3 plugs that are on here. So I'll kind of point to those. We have 1, 2, and 3. And up here in the top section, you can actually hook a magnehelic to measure the pressure differential. And this does qualify as a testable backflow preventer. Now, it's not an RPZ backflow for commercial applications, or there are some jurisdictions that require a reduced pressure zone assembly backflow. Those are significantly more expensive. This doesn't qualify for that, but for those jurisdictions that do need a testable backflow, or that just want to step up to a higher quality serviceable fill valve and backflow, this product fits those needs. We also offer it in 2 different configurations. So one part number will include both sweat and threaded tail pieces in the box. We also offer this in a press configuration. So it's 2 different SKUs, kind of pick if you want to press it or if you want to use sweat and thread or a combination of the 2, and you can get set up from there. Now, one thing that I want to touch on with honestly both of our fill valves is when you do your initial fill and your initial purge, my strong recommendation is to shut off the water makeup. So you can do it with the left-hand ball valve here on this device, or a field installed shutoff valve on the previous fill valve. The reason I suggest doing that is I have seen many hydronic systems where, let's just say you're doing a radiant in-floor system. I've seen the people that come in, the trades after, that will pop a nail right through the tubing. And the funny thing about nails in hydronic systems and in PEX tubing is they will hold pressure for a certain period of time. After about a year or so, that nail will eventually start to rust, and you'll start with a drip, which will turn into a larger drip and then a major water problem. If you leave your fill port open, what will happen is it will mask that problem until it's a big problem. If you shut it off, as that nail starts to become a small leak, it will actually drop your pressure, indicating that you have an issue with the system. Once you fill your hydronic system, and I'll kind of show you how you do that here in a moment, but once your hydronic system is filled, you really should not ever have to add more water. There are certain things that can happen that will allow elimination of water, but really once it's filled, it should be done. So I personally am a big component of shutting your water makeup off. And it's true that on a big system, when you fill it, as the air bleeds out, you will lose some pressure, but I'm a big fan of being safe, and once it's purged that initial air, I recommend shutting that off. I want to touch on pressure settings. So both of the fill valves I just showed you have pressure ranges from, they vary a little bit, but roughly 8 PSI to 50 PSI. If you look at any of the old boiler manuals, you'll see just about everything is set up with 12 pounds. That's just kind of the number that's been used for years and years and years. It works in most applications, but I want to point to what happens when you change your static pressure, what you change the filled pressure to. When we use 12 PSI, there's a formula here that I want to identify because this is the formula you're going to use quite a bit. And that's 1 PSI is equal to 2.31 feet of head. These 2 numbers are used in hydronic heating systems in varying components. So pumps a lot of times will reference feet of head. Static pressure, your fill, will reference PSI, and sometimes we go back and forth. So in this example, I want to show you 12 PSI, and I'm using an example where the boiler is down in the basement, which is predominantly most of the hydronic systems that get installed. If the boiler is down in the basement, if you stack that to 12 PSI at the lowest point, that's going to allow you to have pressure up to 27 feet. When you get beyond 27 feet, you essentially run out of pressure. And the problem with that is now if you have any automatic air vents, it will actually start sucking air back into the system. So you want to make sure that you maintain positive pressure throughout the hydronic system. So if you have to go taller than 27 feet, or if you're even questionable about that, I strongly encourage you to raise your static fill pressure up a little bit. And it doesn't take a lot. So in the example I've got right below there is if you were to take it and go to 15 PSI and you multiply by that 2.31, now just by increasing it 3 pounds down at the fill, you now have the capabilities of going almost 10 feet taller vertically while still maintaining positive pressure. So I'm a big fan of bumping it just a little bit. 15 PSI has also seemed to become more of the new norm. There's more and more people starting to do that. Part of the reason is a lot of the newer boilers, depending on brand, some of them have much more sensitive pressure cutoffs. So I've actually seen a couple that will lock out if it drops below 10 PSI. So if you fill it at 12 and your boiler locks out at 10, it does not give you a whole lot of room for cushion there. So 15 PSI is my recommendation. You can do whatever you want. And I'll talk about the fill here in a little bit more as what happens if you go over some pressure settings. When we look at filling, the initial purge is one of the most important parts of the hydronic system. Obviously, you want to make sure there's no leaks and you want to make sure your layout is done correctly. But if you speed up your initial purge process, you're going to end up with air collecting in pockets, which will act like basically wall blockages. My recommendation when you start filling a hydronic system is to go not only zone by zone, as I'm showing in this image where you're just pulling through one specific zone, but also go loop through loop. So let's say hypothetically that one zone valve fed a remote manifold with 4 loops. My suggestion would be while you're draining through here, through the fill valve, go up to the manifold and go every single loop one at a time. And the reasoning is water takes the path of least resistance. So if you weren't able to lay out your tubing to where every loop is exactly, let's just say 160 feet, let's say you had 3 loops at 160 and you had one that was 220 feet. There's a good chance if you have all of the loops open at the same time, you're not going to purge properly through that longer loop. Because again, water is going to take the path of least resistance. Those 160-foot loops don't have as much resistance through the piping. So there's a good chance you're going to be purging through those first 3 great and never get that 4th loop, that longer loop purged properly. So my advice is to go loop by loop by loop as you purge through here. You also, again, water will take the path of least resistance. So you kind of have to direct it. So if you look, the ball valve that's above the boiler is shut off so that when water comes into the system, up into the air eliminator, it can't go right in a clockwise motion to the drain. It has to go up through the zone, through the loops, into the boiler drain and out the bucket. So you kind of have to direct and force your water flow through ball valves. As we get into another incredibly important piece of the hydronic system, and this kind of ties into all the pressure that we've been talking about, we get into our expansion tanks. An expansion tank is absolutely required on every closed loop hydronic system. Our expansion tanks have half-inch tappings because that's typically the same pipe size that you have doing the water feed. It's also coincidentally the same half-inch tapping that we have going into the bottom of our air purger or SuperVent, which is our air elimination device. These all pretty much come pre-charged at 12 pounds from the factory. They can handle 100 PSI, which is far above and beyond anything you'll ever see on a residential system, or I should say should ever see in a residential system. And one thing I'll note when you do this, when you fill this system the first time, before you install your expansion tank, I said that they come pre-charged to 12, but if you remember back a couple minutes ago, I talked about how more and more people are starting to move into a 15 PSI static pressure. Well, if you put an expansion tank on that's charged at 12 pounds to a system that's charged at 15, you're preloading the air or the air side of that expansion tank. So when you install an expansion tank, before you hook it up, you want to take an air pump and you want to pump the bottom of that expansion tank up to the pressure you're going to run your system at. So if you're going to run your system at 15 pounds, you want to pump it up to 15 pounds. That will create the same pressure on the air and the water side, which will allow full absorption into the expansion tank. The reason that's important is water expands as it gets hotter. So if you fill a system, and let's just say it's cold when you fill it up, you're in a cold climate, it's 45 degrees. When you go to kick that boiler on, theoretically, that boiler is going to go from 45 degrees all the way to 120, 130, whatever your system design is. As it heats up, it's going to expand. You have to have somewhere for that to go. Otherwise, your pressure is just going to go up, 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 up until it hits the relief valve setting on your boiler. Most residential boilers are set at 30 PSI relief, meaning if your pressure ever hits 30 pounds or close to 30 pounds, it's going to bleed out through the relief valve. So a few things will happen if that takes place. One, it's going to, if let's just say hypothetically you did take my suggestion and shut the water feed off, when the relief valve pops at, let's say 30 pounds, it's going to be under a higher temperature situation. So the relief valve is going to go off until it equalizes the system pressure at 30 PSI. Then the water is going to eventually cool down once the boiler satisfies. The problem now is, as the water cools down, you're going to lose your pressure because, again, it had nowhere to go. So as the pressure drops, now you're going to go below the minimum required pressure to fire the boiler for the second time. So if you ever go to a job site that has low pressure, the boiler's tricked on low limit, etc., or not low limit, but low water cutoff, there's a good chance that the relief valve blew, and that's the culprit. So first thing I would do is check your expansion tank. That is usually the reason that you run into those type of problems. And again, the expansion tank is there to regulate your pressure. So the bottom of every single residential expansion tank has a Schrader valve, same thing you have on your car tire. Again, pump that up, but a couple things you can do to check and see if the expansion tank has failed. First thing, knock on it, just like it's a wall. If it sounds hollow, chances are that expansion tank is fine because you're knocking against the air cushion inside of there. If you knock on it and it sounds full or waterlogged, you have reason to be concerned. If you go down to the bottom of the Schrader valve and you depress that and you have a bunch of water coming out of there, that means your expansion tank is dead. Basically, the diaphragm that is separating it has cracked, ruptured, etc., which is causing all the water to essentially displace the air cushion that you have down there in the bottom. Pretty easy to tell. They also become incredibly heavy as they're waterlogged, but that's the easy giveaway for the expansion tank is if you depress that Schrader valve at the bottom and you get a bunch of water coming out, that's the dead giveaway. If you get just a little bit, it's probably just condensation, but if you get a bunch of water pouring out of there, that expansion tank's dead. Use that as a last resort because if you depress that, you get a bunch of water coming out and they find out that it's not that bad, it's just mainly air. You have now let all your pressure off the expansion tank, and the only way to properly repressurize it is to unscrew it from the system, pump it back up, and screw it back in. The other thing I want to talk about, and this is more for the pump placement, but I wanted to reference it here, and since we're talking about a lot of these type of topics, is where the expansion tank goes in reference to the pump. I see this done incorrectly a lot. But when you look at your expansion tank and your fill valve port, because most of these components are tied together, this is considered the point of no pressure change, point of zero pressure drop. So what happens is if you fill this system, and I'm going to go back to our 12 PSI example, if you fill it to 12 PSI, you have 12 pounds on the expansion tank, both on the water side and the air side, what's going to happen is when your circulator comes on, the whole point of a circulator is to create a pressure differential to drive flow. So if you pump into an expansion tank, and let's just say in order for that pump to kick on, let's just say it's going to create a 14 PSI differential. Little extreme for a residential system, but it helps sell the image that I'm trying to paint here. If it's creating a 14 PSI differential and you're pumping into the expansion tank's purpose is to absorb any kind of pressure change. So what you're doing is you are entering the expansion tank, you're basically pumping against that bladder. You've now got 12 pounds coming out because that's the expansion tank is doing its job. Well, in order to have that 14 PSI differential, it is basically creating a negative pressure on the suction side. As I talked about earlier, if you create negative suction, one of the major drawbacks is any point where you can introduce oxygen, you're going to suck air back into the system. I'm going to talk about why that is so, it's not good. So if we look at moving your pump to the pumping away from the expansion tank, so move the suction side after the expansion tank, it's going to create that 14 PSI differential. What you're going to do is you're now going to have 26 PSI on the outlet of the pump, and then it's going to bring it back to 12 at the expansion tank. So you're basically putting a little extra oomph on top of the system. But what it's going to do is you're now creating a situation where you're helping air eject out of the air vents. You're preventing the air from getting sucked back in. And also by putting a little bit extra pressure in there, and we're not going to talk too much about this, but by creating extra pressure, you're helping prevent cavitation inside the circulators, which is one of the big killers of pumps, especially wet rotor circulators. When we look at our expansion tank, when you size a hydronic system, you want to make sure you don't oversize components, because if you oversize your boiler, it'll short cycle. If you oversize your pump, it's going to work outside of its duty curve. If you oversize an expansion tank, nothing bad happens. So if you're ever on the cusp of getting an expansion tank that's a little too small or a little too big, always go bigger. It's not going to hurt anything, and the price difference from one size to the next is pretty negligible. So when you're looking at expansion tank sizing, the best way to calculate what size expansion tank you need is to figure out how much water you have in the system. It's not that complicated. A lot of people get really nervous when they have to figure all that out, and there's not too much to it. So when you look at how you calculate the water volume in a system, look at your main components. So I'm going to go back to an in-floor radiant system. There's a couple of things you got to add up. You got to look at your boiler, which most of the newer boilers have less than a gallon of water inside of them. You can look at your loop that you have, and I just grabbed my calculator. I'm going to go through an example real quick. But let's just say in this example, we're going to have 1.25" boiler piping, and let's say I've got 60 feet of it. So if I have 60 feet of 1.25" pipe, I've got a table that I put together down here in the bottom right that you can pull off. All this information is available on the internet or in the PEX design manuals. They usually have this posted. But an 1.25" copper type L, we're looking at 0.065 gallons per foot. So if I have 60 gallons and I multiply that by 0.065, I've got roughly 3.9 gallons of water in my boiler loop. So we've got, let's just say, a gallon in the boiler. We've got 4 gallons in the system loop. We're up to 5 gallons of water so far. Well, now let's say we've got 3 remote manifolds, and we went 3/4 inch piping from the boiler room out to the manifold and back. So if we used a total of, let's say, 500 feet of 3/4 inch PEX, I've got those tables marked there too. So 3/4 inch PEX is going to be 0.0189 gallons per foot. So 500 times 0.0189, I'm looking at 9.5 gallons. So the supply and return piping has 9.5 gallons. So then the other one, again, this is an in-floor job. So let's say I've got 5,000 feet of 1/2 inch PEX. Pretty standard size being used for in-floor. So I got 0.0096 gallons per foot times 5,000 feet of PEX. I got 48 gallons there. So if I add up 48 plus 9.5 plus 5, I'm looking at 62.5 gallons of water in the hydronic heating system. So the next question is, what type of system is it? Is it in-floor? Is it staple up? Is it gypcrete? All of that matters because they're going to have different design temperatures. If we look at something like a standard in-floor gypcrete job, we're looking at probably never exceeding 125 degrees. Again, these are all general rule of thumbs. So what we can do is we can come down to our chart that I show in the top left. You're going to see our 4 most common expansion tank models. So our TK 300-15, -30, -60, and -90. And you'll see at the varying temperatures on the left. So we're going to, I'm going to make it easier. We're going to figure 130 degrees max temperature. If you follow that across, our model 15 can handle 58 gallons. So our general rule of thumb, we said there's probably close to 62, 63 gallons in our system. I don't want to use that 15 because I'm a little bit too close to that. If we jump up to the next size, we go to the 30. The model 30 can handle 128 gallons. That is double the estimated volume that I have. That's the one I'm going to pick right there. And you'll see as the temperature goes up, the expansion tank can handle lower volumes. And again, that's because the higher the water temperature, the more expansion you're going to have. So a lot of times it's pretty easy to rough estimate, because if you're doing a new construction job, you know how much 1/2 inch PEX you bought, you know how much copper you bought, you know how much, let's just say hypothetically 3/4 you bought. So it doesn't have to be exact. Always overestimate this part, and you can get to it pretty quick. Even on retrofits, a lot of times you can go in and look, the PEX manufacturers, if it's an in-floor job, will have it marked on beginning and ending footage, so you can kind of calculate the loop lengths on each manifold. And if it's doing baseboard, it's pretty much just all 3/4 copper. So you just add up how much linear footage of piping you have in the system, and you can kind of work backwards into how much water volume you have. This is my favorite way to calculate it. We do have some general rule of thumbs that exist. I'm not a huge fan of these because a lot of times this is using much older technologies that have been a little bit obsolete from the sizing standpoint. So these tables do exist. We back them, we support them, but my personal opinion is try to get an estimate on the water volume and calculate it out from there. The next critical piece that every hydronic system needs to have is a main air elimination device. We've got a couple of different configurations for this. We have an air purger, which is sometimes referred to as an air scoop. We also have our SuperVent, which is a microbubble air eliminator. Before I jump into the two devices that we sell as your master air elimination product, I want to talk about really where air comes from and what happens if you don't get it all out. So I talked initially about the taking your time when you're doing the initial purge. So when you're doing the initial purge and really filling the system, you're basically displacing the open piping with water. The problem is when you fill from the city main, you're going to get a water and air mixture. If you go to your faucet and open it up, the reason it doesn't come out perfectly clear is because you're getting an air and water mixture coming out of there. It's the same thing when you fill and purge. If you purge every single line and then you turn the system off, you've got all those little micro bubbles which are eventually going to collect together and create one giant bubble. So that's one of the biggest culprits for where air comes from, is actually when you initially fill it up, it's entrenched with air just from the properties of filling. The next, I'm going to talk about PEX, and I hate to pick on manufacturers. I'm not even picking on them, but I wanted to bring this up because Wurzbo has a real big presence, or Uponor. They make two different lines of PEX, right? They have AquaPEX and HEPEX. You need to make sure that you use HEPEX because it has an oxygen barrier. If you use the AquaPEX, it is significantly less expensive, but the problem is you're actually going to get oxygen molecules traveling through there. They call it oxygen permeation, which is just constantly going to be infiltrating your system. There's no remedy for that. And typically once your PEX is installed, it's installed. If you don't take care and get rid of all the oxygen, what you're going to run into is you're going to have oxidation on parts, pieces, etc. And I've got an example here. This is actually a boiler chemical company that they're using as an example where they have some corrosion inhibitors. But this is a perfect example to show what happens in systems that do not have the oxygen properly treated. On the left-hand side, you'll see a jar with some pretty common fittings that you'll see in a hydronic system. So we got a black iron nipple, we got some copper component, some brass. You could throw some stainless steel in there if you wanted. And then that's after it's had a chance to kind of sit in oxygenated water. If you go over to the right-hand side, you can see what's happened over time. It basically becomes mud. Well, I don't know about you, but I don't want mud going through my circulators, through my boiler heat exchanger. It's going to cause corrosion. It's going to cause decreased performance when you look at heat transfer, all kinds of things. So you want to make sure you get all the air out. Our air scoops, our air purgers, we've had for a very long time. They're made from cast iron. They're big honking pieces of metal, basically. Very inexpensive. We offer them in our product portfolio from 1 inch to 1.5 inches. And what you do is you install an air vent, automatic air vent at the top of them. Again, we have a 1/2 inch connection at the bottom because that's typically where the makeup water is fed into. There's a few things that you need to pay attention to with this. So in the way that this operates is you have to have probably at least 18 inches of straight pipe before it, because what you need to happen is you need the air bubbles to float up to the top of the piping so that when it enters this device, it's going to basically get scooped up through those veins and driven up into the automatic air vent. In order to do that, your velocity has to be relatively low. So ensure that you don't have any more than 4 feet per second. And you also need to make sure that you got enough straight pipe before, because if you 90 right into this, you're going to get a lot of turbulence, which is going to prevent that air from rising up to the top. The problem is with this type of a design, it works fine for baseboard that's done with copper tube or copper fin or cast iron boilers, because real large water passageway is a lot of volume there. But as we've moved into high efficiency boilers taking over a big portion of the market, PEX with small diameter tubing being utilized. All the little micro bubbles that you see coming through the end create noise issues. They also create a lot of problems for the boiler itself. So we have seen a massive transformation away from the air scoops that I just showed and into the SuperVents. The way these work is, instead of relying on air floating up to the top, it catches up against we use what looks like a stainless steel brush. So as the air bubbles come in, they kind of get caught on those bristles. As enough of them collect together, they float up to the top. When you get enough of them floating up to the top of the SuperVent, it's going to push that float assembly down, which is going to pull the shutoff mechanism back and allow the air to automatically purge off. This is the way most of the air vents work. And one thing I do want to stop here, because this is a great illustration, and talk about is, I had mentioned not every system very early in the presentation. I mentioned not every system has a fill valve on it. The reasoning you don't do that is, let's say you've got a snow melt or an ice melt system, or you've got some tubing that's running outside, you have to run antifreeze in it. I'm personally not a big fan of antifreeze in anything unless it's outside. The reasoning is glycol antifreeze has to be maintained. It breaks down over time. The other reason is it will gum up your air vents like none other. So if you've ever played with it and spilled it on your hands, anybody that's ever done a glycol system knows what I'm talking about here. It becomes sticky, becomes really tacky. And the problem is with that float assembly, it has to be able to slide up and down. Well, if you start to create, and it becomes tacky when it is introduced to oxygen. So where's one of the few points in the hydronic system where it's constantly going to be around oxygen? It's up at the floats on all your air elimination devices. So in glycol systems, you'll see some of these floats that'll start to stick. Now, our engineers have reworked the float assembly on our SuperVents about roughly 15 years ago. So they are much less prone to sticking problems than a lot of the vertical vent that our system used to have. So you see ours vents out to the side. The beauty with our SuperVents is we use the exact same float assembly from 3/4 inch to 2 inch. So if you ever have an issue with the float assembly sticking or not venting, you can unscrew it, and it's the exact same configuration across all of the sizes. Makes it really easy to keep one on your truck, etc. But glycol is pretty nasty on a lot of your air vents. When we jump into our air vent portfolio, these are not your main air elimination devices. So an air vent goes on the high points of piping where you're going to have air bubbles collect and rise together. You'll see these a lot on boilers. You'll see them on fan coil valves, on manifolds, anywhere where if your system is shut off, it has a chance to collect together and rise up just through buoyancy. That's where these devices should go if you have a risk of not being able to purge through. And I'm actually going to jump back a second. So I want to say one other thing. When you first fill a system and you shut off that water main, I also advise running your circulator for a while. The reasoning is, I will reference this to an analogy because I know we have a lot of people on the call today that have HVAC backgrounds. If you look at an air filter in your house, and let's say you put in something that's very effective at collecting all the junk in the air, and you never run your fan except when there's a call for heating or cooling, it's not going to do hardly any filtering. It's the same process with this. If you put in an air scoop or a SuperVent and you never run your flow through it, it's never going to get a chance to capture the bubbles. So when you do your initial purge, you don't need to worry about the boiler unless it's cold. Run your pumps. Just turn them on, let them run for a day or two. Because what it'll do is it'll force circulation through all your zones, through all your loops, and really drive all those micro bubbles and make sure they get eliminated from the get-go. Because again, what will happen is if you get enough of these bubbles that collect together, they're going to create basically an air dam in the piping. And the circulators that we use, especially residentially, don't create a big enough pressure differential to push those air pockets out of there. They basically just become like blocks in the piping. The only way to get those back out is to go back through the fill valve and drive high pressure to push those out again. So air vents, jumping back to where we were, these go at the high point. We've got a few different configurations, and I wanted to touch on some of these because I really like a few of our air vents. The first is our SuperVent top. If you'll notice how it's got that 90-degree exit, These are great for high capacity areas, spots where they're going to be running a bunch, because it's basically a high capacity air elimination device. The EA series are my favorites. If you have glycol systems and you have air vents, I strongly recommend using the EA series. And the reason is it's got a built-in shutoff valve. If you twist the top part 90 degrees, it's almost like having a ball valve that's going to shut off and give you the ability to unscrew the top, access the float, either clean it off, typically just with water and soap, put it back in, or I have a lot of people that just replace the whole guts. So they'll just walk in with a new valve, unscrew it, and plop a whole new float assembly in. You twist it 90 degrees back, you haven't had to drain down any of the system, you've cleaned your vent, you've fixed it, you're back in operation. They are a little bit more expensive than our standard gold top. Our gold top, we offer an 1/8 inch through 3/4 inch. That's just your basic air eliminate, basic auto air vent. They work fine, but again, there's no way to service them. So if they start leaking, again, typically it's that float assembly that'll get stuck in there. There's nothing you can do other than remove it and replace it. We do also offer a max event low profile. These are great if you're having to put air vents in baseboard enclosures or in real small spaces. It gives you the ability to get into that really small area. So we've covered so far air elimination, fill valve, backflow, and expansion tank. Well, as I had mentioned, those 3 parts are needed for every single boiler. We have gone and prepackaged this for you. So if you grab a boiler, you can grab one of our boiler trim kits. It's got our expansion tank, our fill valve and backflow, our air separator, and we also include an expansion tank check. So what that does is a little device, kind of like a preloaded check valve that you can screw on the expansion tank. So if you do have to service your expansion tank, as you unscrew it, it's going to put that little check in place, which will prevent water from coming out of the system, allowing you to grab another expansion tank and screw it right back in without having to isolate or drain anything down. We've got these in 1 inch and 1.25 inch sizes, which is built around the SuperVent, or we do make these in an air purger as well. And then we have sweat or threaded configurations. And here coming soon, we will have a press configuration as well. One piece I wanted to touch on is a third method of air elimination. So I've talked on air vents and our super vents. If you'll look at the 2 schematics that I have up here, the left-hand side, this is the image that I've been referencing so far in the presentation. On the right-hand side, you'll see what's called a hydraulic separator. I'm giving everybody on this call a little peek behind the curtain right now. These are coming very, very soon. We will have more detailed information on these, but I want to give a little bit of a teaser. Most of the newer boilers, modulating and condensing boilers, request that you pipe them in a primary and secondary configuration, meaning you want to separate the boiler flow from the system flow. This is done inexpensively through what's called closely spaced tees, and it allows you to run variable flows out here, fixed flows around the boilers, or vice versa. Lots of different dynamics and situations that can come up. But when we look at this, one of the biggest problems I have seen just from going out and helping people in the field myself is that when you pipe it with closely spaced tees, it can create, well, the whole purpose is to create a hydraulic separation, but what it is very particular on the install. And when we say closely spaced tees, my perception of close and your perception of close could be dramatically different. I've been on job sites to where, if you'll see here at the bottom, these tees, the center of these tees are supposed to be 4 times the pipe diameter, not to exceed 12 inches, but really the closer the better. And the reason is that there's so little pressure drop through here as this pump, let's just call this our boiler loop, kicks on, it's going to go right through here because, again, water takes the path of least resistance. So if these are right next to each other, there's no reason for the pump to push any water up here because it's going to be harder. And same thing with the other side. If these 2 tees are together, when that pump creates its pressure differential, there's no reason to drive any flow out here because it's going to be harder than just driving it right back through. I'm actually showing it backwards. But, oh, let me go back a slide. Sorry about that. So these tees, it's a necessity for these tees to be very close together. It also is helpful if you can install a ball valve here to help with purging, but that can create a whole nother set of issues, because if you install a ball valve here, now you've created a pressure resistance. So you'll see all the different requirements. So going into the closely spaced T, you're supposed to have at least 8 times the pipe diameter going into it. Then your 2 T's are supposed to be no more than ideally 4 times the pipe size diameter. And then after it, you're supposed to have another 4 times the pipe diameter of straight pipe. I have been out to jobs with closely spaced T's to where the middle of here and here is closer to 2 feet. Well, that doesn't work right. And what happens is now when this pump kicks on and this pump kicks on, they're actually feeding into each other, which is going to screw up the flow characteristics around both the system and the boiler. And it's also going to, over time, sacrifice the weaker of the two. One of the 2 pumps is going to get chewed up. So this can be done. It's very cost effective, but it does leave a lot open if there's any issues. If we look at a hydraulic separator, it takes the place of the closely spaced T's, plus it combines several other functions. The first is air elimination. If you use our hydraulic separator, you do not need our SuperVent, because it will actually take care of the air elimination inside of it. What happens is, as water enters the hydraulic separator, the velocity is going to drop dramatically, close to, not exactly, but close to 10-fold. So if you're running a flow velocity of 3 feet per second and you enter this vessel, it's going to drop to roughly 0.3 feet per second. So a few things happen when that takes place. First, air bubbles, because of the dramatic drop in flow velocity, air bubbles are going to float up. They kind of get caught against this baffle and float up to the auto air vent. Dirt, as it travels through the system, will fall because, again, the flow velocity change. On top of that, our hydraulic separators are going to include a magnet. This is a rare earth magnet, very strong. We will be talking a lot more about these in some future webinars, but it allows for separation of the magtite. And really, as we've moved into systems with variable speed circulators, that is becoming more and more of a problem, because all of those ferrous metals that are left in the system, as we use variable speed pumps use permanently magnetized motors. So when that pump kicks on, it's basically a giant magnet. So all of that junk, that ferrous metal, is going to basically get sucked into the pump. Well, you guys can imagine what happens if you've got junk in your pump. It's going to chew it up. So what we do is we use a magnet at the point of interchange between the boiler loop and the system loop. Now we're going to stick all of that junk in a point where it does not matter. This is serviceable, so as your system runs, you can isolate it. This will all be in the install manual on how to do it, but you can isolate it and actually drain all of that out of there. You pull the magnet out while there's no flow, and it's going to fall and draw right through the drain valve in the bottom. So it eliminates the need for the closely spaced T's. It takes the place of the SuperVent air eliminator. It adds magnetic and dirt separation, which is becoming more and more critical with more modern systems and system components.
Thanks so much, Chris. We appreciate you walking us through that hydronic systems overview. We're going to transition to answering some common questions about hydronic systems that you may find helpful. If you are looking for more information on any of the products that you have seen Chris preview for you today, you can visit the new resideo.com/pro website for additional information. As a reminder, if you do have any questions on anything that Chris reviewed today, please take a few moments and enter that information into the Q&A feature that's in your Zoom controls at the bottom of your screen. We'll do our best to answer and address any of those questions in the time that we have remaining. Joining us for our common questions in our Q&A section, we're going to have Mike Ortiz, who is one of our water inside sales reps with Resideo. He's going to join Chris to help answer some of your questions and help with the common questions with Chris. Thanks for joining us, Mike. We seem to have some
Mike might be having
audio.
some tech problems.
Okay.
With that because I know we're a little short on time, I want to get through some of these. So I'm going to ask the questions to myself. So these are
Okay.
some questions that we
Oh,
get.
there's Mike. We can hear
There
you
we
now.
go. There we go. Thank you, Jamie. And so let's start off with the first one. How do I check the pressure in the expansion tank, Chris?
So Mike, this question comes up actually quite a bit. So really the only way you can do it is to disconnect the expansion tank from the system. So on a new install, it's a piece of cake. You basically just throw a floor pump that's got a gauge, or you can screw like a tire gauge right onto the bottom of it, and it will show you what your air pressure is in the bottom. The problem is, as I mentioned, it has to be disconnected from the system, because if not, you've got your system influencing the actual air volume inside of there. So it's going to basically push against it. So just a tire gauge basically at the bottom, but it does have to be disconnected to get an accurate read.
Great. How do I know if the expansion tank has failed? I think you touched on this a little bit, but why don't you touch on it again?
Yeah, so this comes up from time to time, and really what happens is the diaphragm cracks or ruptures, and there's a few different things you can do. First, the relief valve will go off frequently. So if you left your water main open, you're basically reintroducing air and water every single time that it does that, which is going to cause a whole plethora of problems. But if you have it isolated, the biggest indicator is you'll see kind of moisture around the relief valve, assuming you got out there fast enough, or by the relief drain. And then the quick check is to kind of hit the Schrader valve on the bottom of the expansion tank, because if you get a bunch of water pouring out of there, that expansion tank is toast. So you don't really fix them, you just replace them.
Good deal. How do I service the air eliminator?
So good question. And we've got three different air elimination devices I could talk on. So the first is the air purger. So you've just got an auto air vent on the top. So that one's pretty easy. Just replace the auto air vent. If you look at our SuperVent, there's really the only thing that ever fails in them is the float assembly on the top, as I had mentioned. So if you unscrew that float assembly, it's the same across all the sizes. You can clean it and put it back together, but what most people do is just replace it, because if you're going to open it up, it's a fairly inexpensive part. Why not just put a new one back in there?
Awesome. I think you kind of answered this next one. Can I service an air vent?
Yeah, well, quick answer is no, unless you're using our EA series. Our EA series can be isolated, and the float assemblies can actually be removed and reinserted and put right back into operation. So quick answer on a normal air vent, no. On our EA series, yes.
Great. What do I do if there is water coming out of the vent port on the backflow?
Scream.
Yeah.
No, the first thing you want to do, if you got water coming out of the vent port, it's an indicator that you got a problem with the backflow device. Most of those you can't get in and service. So the problem is you really just have to take it out and replace it. We do have a sediment screen prior to the inlet of the backflow, and I'm referencing our BP900, but there's not a whole lot you can do to repair those. They're pretty inexpensive too. So if you do see those start to fail, just rip it out and put another one in. On our NK300S, different situation. That one you can't isolate. You've got two isolation valves there, and I can't remember the size tapping. I think it's a 1/2 inch on the top. You can unscrew it, access the filter screen, the check assemblies, clean them, and put them back.
Great. Why does the boiler relief valve keep going off?
Several answers to this. One, the relief valve has failed. That could be a potential problem. And then two, usually it's because there's a pressure issue. So either you've overpressurized the system, and when the pump kicks on, it's creating so much additional pressure that it's basically going beyond the setting of the relief valve, which again, most of them residentially are 30 pounds. The other culprit could be the expansion tank. If the expansion tank is either undersized or flooded, it's not going to allow for proper expansion, which is going to bleed the relief valve as well.
Awesome. How do I use the fill valve for purging, and how do you prevent air pockets if the pump is at the low point in the system?
So I think I touched on part of this. The fill valve, let's just say we're using our VF06. So what you're going to do is The best way to do it is to open the pressure all the way. So on our VFO6, I believe it goes to 50 pounds. On our NK300, I believe it's 58. But you just open the pressure all the way up. And then you're going to use the isolation valve to open or close as you're purging through areas. So again, loop by loop, take your time. Do not rush your initial fill. But as the water goes through, let's say the VFO6 that has the little screw valve on the bottom, you're just going to open it all the way up, which is going to allow that full 50 PSI through. When you're done purging that loop, you start shutting that down, isolate that loop, and move on to the next one. Once you get all your loops purged, you basically shut that down, you open it up, and adjust your pressure on the VFO6 to whatever you want the static fill to be.
Great.
Oh, and I'm sorry, there was a second part to that question. How do you prevent air pockets if pump is at the low point? That actually shouldn't really matter. It doesn't matter if you're filling at the top or at the bottom. If you're filling at the top, you're going to have the additional impact of gravity. So it's going to give you more pressure at the bottom. But again, most of the systems in the US are done in the basements. So if you fill from the bottom, you're going to have 50 PSI going up. So as long as you're not going too tall vertically, it should not be a problem, because your 60 pounds or whatever you have coming into the system should be more than adequate. But I have been on some commercial high rises, and the problem is if you're bringing 50 pounds into the bottom and you got to go 14 stories tall, you're going to have a major problem getting pressure. So you end up having to create water introduction points at the very high point so that you can have enough pressure going through to get all the way to the bottom.
Right.
And then I believe we've got some live questions as well.
Yes,
Mike,
sir.
if you want to ask
Sure.
some of these.
How often should the relief valve be replaced? I can take this one, Chris.
Yeah, sure. If you want to take, yeah, absolutely.
So typically, you know, if you're doing service on a system and you're there annually, you should be testing that relief valve. Now, if you walk into a system that has been sitting there, the manufacturers recommend that from the data manufacturer, you are replacing that valve every 5 years. Okay, the second question is it best to have the pump on the return? Why don't you take this one, Chris?
Sure. So I'm going to give kind of a cop-out answer on this. It's always best to check your boiler manufacturer install guide. But with that being said, the pump placement is incredibly more prevalent in reference to the expansion tank. So if you have your expansion tank on the system or the primary loop, it's the most important piece when it comes to pump placement is making sure that it's on the discharge of the expansion tank. You always want to pump away from the expansion tank. So as far as having it on the return of the boiler or the supply of the boiler, reference your boiler install instructions. And then if it's on the system side, you would technically actually want it on this. Again, it would depend on where you put your expansion tank, but usually I see expansion tanks placed on the supply of the system. So you would put it right after that. It's really just make sure you're not pumping into the expansion tank. You want to get that pump as close to the discharge of the expansion tank as you can.
Great. Another question came in. How about checking the pressure on the expansion tank if no isolation valve to disconnect the tank on the system, on the existing system?
Pressure. There's not really a good way to do that, to be honest.
Yep.
Mike, I don't know if you have any tricks up your sleeve, but if the expansion tank's on there, it's an existing system and there's no way to isolate it, I don't know that there is a good way to check your pressure.
There's not. I mean, yeah, the closest you're going to come to it is what you talked about. You hit the Schrader valve a little bit, and if we get water out of it, you know, there's an issue. If it's a little bit of water, at that point, if we don't have a way to isolate it, there's going to be some purging involved. I mean, you go to the closest shut-off valves you've got and isolate whatever section of piping you can and remove the tank and do whatever drain down and refill and repurging you got to do.
Yeah, that's kind of what I've seen as well. The other thing that I didn't really touch on that I'll bring up with expansion tanks is not only do you want to make sure you pressurize it because the change in elevation can impact the pressure because I think they're pumped up to 12 pounds at sea level. So you want to make sure you pump it up at whatever area you live in. I'm in the Denver area, which, you know, we're a mile high, so the pressure is going to be a little different. The other thing that does come into play that I've seen impact in a negative light is you need to make sure that you pump it up in a condition similar to what the mechanical room will be. So if you pump it up in your truck and it's -5 outside, and then you put it in a mechanical room, well, it's just like the air in your tires. So as it heats up, you're going to get expansion, which is going to basically add more pressure. So you want to try to pump it up in a condition with the same temperature as well.
Great. Can hard water affect these systems such as boiler, and is there any preventive maintenance?
Oh yeah. In short, absolutely. Water is basically the lifeblood. It's our blood in the hydronic system. And if your blood's dirty, it's not going to work. So glycol systems add corrosion inhibitors. But again, I had mentioned I'm not a huge fan because glycol breaks down over time. Certain situations you have to use it. But there are boiler chemical companies that you can introduce. And I strongly encourage you to use that on every boiler system. I hate mentioning other manufacturers, but Fernox is one of my go-tos. A lot of distributors have Fernox. There are other brands out there that I'm sure work just as well. I'm just more familiar with theirs, but they have cleaners, which you can introduce and basically clean all the piping so it gets rid of any flux or anything that you have in. Plus pipes, when you buy them, are going to have dirt and junk in them just because. And then, so you can clean it out, and then they make corrosion inhibitors that you can introduce into the system. So strongly encourage that. Those mason jars were a perfect example of why you want that. So it really helps prolong any damage in the system.
Great. So I'm going to take this last question. In reference to the pressure tank, is hooking the pressure gauge suffice to verify pressure while in loop to the operating system?
Hooking the pressure gauge. I don't know if I completely understand that question. Is hooking a pressure gauge service?
You know, your triadicator is going to give you a system pressure while you're operating. And, you know, most of them are pretty decent for giving you the operating pressure of what's going on at that moment. You're going to see some variation as the system heats up and goes down. If you don't see a lot of variation to that, sometimes that's a good indicator that something's going on with the pressure tank, especially if we're spiking up. So that's something to also consider.
And I have, Mike, I do want to answer one. I know we're going over time a little bit. I want to answer one more question that came up because I think this is a good one here. So in reference to your early comment about once the system is filled and purged, it should stay closed. What are your thoughts about autofill? So technically, both our FM911 and NK300Ss are autofill devices. They're great because when you do your initial purge, what's going to happen is, again, you're filling it with an air and water mixture. So over time, it's going to bleed out the air that's in the system. It doesn't take a real long time. So in a perfect world, I'd say leave your autofill open and let it do its job for the first, I don't know, week or so, and then go back to the job site and shut it off. Because I love the idea of an autofill. I think it works great in certain situations like the initial fill, the initial purge. The problem is I have seen it more times than not mask a small leak. And the problem with small leaks is you usually don't find them until they're a major, major problem. So after it's done its initial purge, if you're on a job site and have the capabilities of going back a week or two after the system's been up, shut the autofill off because it really will mask a problem.
Thank you to Chris and Mike for answering those questions, and thank you to all of our participants today. Great questions, great interactions, and a big thank you to Chris for sharing his insight during our technical presentation today. Please be sure to join us every Tuesday at 2 p.m. Central Standard Time for our Resideo Customer Webinar Series. Next week, we are featuring a training on optimizing your truck stock for fall. Please be sure to share the details of that training with your teammates or your coworkers and plan to join us next Tuesday. If you'd like more information about our upcoming September series of webinars, please visit resideo.com/webinars and navigate to the HVAC or plumbing tabs for more information on our upcoming sessions. We are also recording these trainings as well, and you can find the recorded versions of these trainings underneath the webinar recordings tab as well. One final reminder to our contractors who maybe did not include your NATE ID on your registration form and you would like credit for today's session, please send your first name, your last name, and your NATE ID to homes.university@resideo.com within 1 week of today's live webinar, and we will go ahead and submit that information to NATE on your behalf. And then 2 final things to note as our training session ends today. You are going to be prompted to complete a survey regarding our webinar session today. Please take a few moments to provide us with your feedback on the technical training that you went through today. We are looking forward to offering these sessions into the future, and going forward, we want to hear your feedback on the session today, as well as any additional topics you'd like to hear trainings on as well. And then you are going to receive a follow-up email from us in a few days that includes some additional information on the details that we discussed today, as well as a link to that website for information on our future webinars as well. Thank you all for joining today's Resideo webinar session on hydronic system basics. Please join us next week on Tuesday at 2 p.m. Central Standard Time for our next session. Have a great day, everyone.